Okay, so with that, we are done with the metamorphic environments that we're gonna cover, and we move on to metamorphic zones. So this slide of metamorphic zones is kind of like a summary of the different things that are going to influence the grade of metamorphism, basically. But in areas affected by metamorphism, geologists are able to observe the usually kind of systematic variation in the mineralogy and in the texture of the altered rocks that now became metamorphic. These different variations that are visible are clearly related to the degree of metamorphism that takes place in each of the metamorphic zones. So, typically, you see a coarsening in the grain sizes as we increase the metamorphic grade, for example. So the figure on the left over here is going to show the progression of shale, which is a sedimentary parent rock, turning into slate, then to phyllite, then to schist, and then to gneiss. And as we have covered before in the lecture, in schistose and gneissic textures, for example, the grains themselves can be visible a lot more easily than in the phyllite and in the slate, where they cannot be visible with the naked eye. So with an increase in metamorphic grade, there's also an increase in the grain size, the crystal size. This type of progression can be seen to have occurred with the metamorphism of rocks that make up much of the Appalachian Mountains, as is seen in this picture on the bottom left, for example. Much of the edges of the mountains, as you're seeing, basically show lower grade metamorphism, but the areas where most of the greatest amount of deformation took place, which is nearer to the center of the mountain building event, those rocks have been greatly metamorphosed, so the metamorphic grade is very high. So you see rocks that have been metamorphosed to low grade on the surrounding edges, again, things like slate or phyllite, but you see a lot of gneissic-like rocks, for example, in areas of Maine and New Hampshire, for example, caused by, again, that great deformation, great differential stress applied at that continental convergence, which caused the differential stress. So in addition to these textural variations, there is also mineralogic variation with metamorphic grade change. So the figure here on the lower right shows the idealized scenario for the minerals that make up and that are common in different foliated textures of metamorphic rocks to occur as. So after having studied many of the foliated textured metamorphic rocks, many geologists have been able to identify the existence of certain minerals that are only present in the rocks that have been exposed to a certain range of metamorphism degree. So, for example, the mineral staurolite right here usually only forms under metamorphic conditions of intermediate to high grade metamorphism. Usually, these minerals that you see right here, or for the most part, right here in the middle area, end up recrystallizing into more stable minerals once the conditions surpass their stability comfort zone, if you would. So they are indicative of a very short range of metamorphic grade. So, for example, slate and phyllite contain chloride, which within this metamorphic grade of relatively low temperatures but still high, and relatively low pressures but still high, is stable. But once those conditions change and there's greater temperatures and pressures, that chloride turns into more like a biotite. And once those pressures and those temperatures are too high for biotite to be stable, it might turn into staurolite or selemonite, for example. So those minerals are very characteristic of only certain metamorphic zones. And so because they're indicative of that short range within the metamorphic grade, we refer to those minerals as index minerals, okay? And they're again characteristic of a metamorphic zone. So as you can also see from the figure, some of those minerals like quartz and feldspar are stable all throughout all of the metamorphic grades. So they're not very good index minerals to determine the zone of metamorphism to which any rock has been exposed. So if I find a gneiss that has quartz, I can't tell it's a gneiss necessarily because it has quartz. I can use other things, but not the fact that it has quartz. Because as you can see, quartz is present all throughout the different metamorphic grades or zones. Okay, lastly, I'd like to talk a little bit about migmatites. So I'm not going to quiz you on this, but I figured I should mention it at the very least. So under extreme conditions of heat, for the most part, but sometimes of pressure as well, gneissic rocks, so gneiss, are triggered to melt partially. So the minerals that melt at lower temperatures, so if you remember Bowen's reaction series, those minerals, at least the silicate minerals that melt at lower temperatures, are usually the non-ferromagnesian minerals like potassium feldspar and quartz. So those minerals that gneiss contains will first melt, and then the ferromagnesian minerals that the gneiss contains will remain in their crystalline form, so meaning they won't melt just yet, they'll still be solid. So you have a rock with some crystal grains, still pure, and then some of the remaining stuff is all melt. However, this rock that has undergone partial melting usually begins to cool again due to the different conditions around the environment, or not usually, but in this case, it will. When it cools again, the non-ferromagnesian minerals will start to crystallize again from that melt that they created. But they will do so in a more kind of igneous texture, so they will look more like an igneous phaneritic texture, where those crystals kind of grow and they're visible to our eye, and they kind of fuse together in a way, but still just crystallize rather than be shaped in a specific banding pattern. So those are going to be the non-ferromagnesian minerals, the light-colored minerals. But the ferromagnesian minerals within that sample were already metamorphosed and were already aligned in bands. And so you end up with a texture that has dark-colored or ferromagnesian minerals that are kind of banded and exhibit a foliated metamorphic texture, and then surrounding them are more non-ferromagnesian minerals, so light-colored minerals that have formed in a more igneous-like texture of just simply crystallizing from a melt. So this is a pretty great rock type, migmatite, to show an example of a rock that cannot be placed in any one group of rocks. So it's partly igneous, partly metamorphic, but is neither one of the two. It has undergone metamorphism and it has undergone partial melting, but not full melting, so it still preserves characteristics of both types of rocks, or rock types, I should say. And this is how migmatite looks. This is it's a pretty good picture, but I would recommend that you zoom in order to look at what it looks like better. Okay, so with that, we finished chapter 8, and we finished covering the main 3 types of rocks. So we'll move on to the remaining chapters that the class will cover. Again, the 3 main types of rocks are going to be talked about all throughout the rest of the lecture. So if you haven't gotten a good handle on them, go ahead and review them. As always, let me know if you have any questions, and I hope that the lecture was clear and that it was instructive.